So we're going to continue talking about transformations. It's the same thing that we did in the last video. So we're going to focus on one problem at a time, figure out what the transformation is, how will the coordinates change, and then actually graph it. All right, so P of x here is equal to negative f of x. Now remember, the f of x that we're talking about here is the standard cubic power function, or x to the third power. And we've got the reference points right here. So what does this negative in front of our function do? We talked a little bit about this with the power functions. This is going to be a reflection. So reflect over the x-axis. All right, so this is going to look a little weird, but if we're reflecting over the x-axis, that means this point up top is going to flip to the bottom. This point on the bottom is going to flip up to the top. What that means for us is our x values didn't change. All right, so no change to x. And we're going to multiply the y value by -1. All right, that -1 will cause it to flip signs and move over the x-axis, whether it's positive, negative, or negative, positive. So our reference point, this first one, we're going to leave the x value alone, but then we're going to take that -1, either flip it sign or multiply it by -1. -1 times -1 is +1. Leave the x value alone, so that's 0. But 0, 0 isn't going to change here because it's not going to reflect. There is no place for it to reflect to. And so if we look at 0 and we try and multiply it by -1, we're still going to get 0. And now our reference point of 1 here, 1, 1, we're going to leave the 1 alone. And then -1 times 1 is -1. So this point, -1, -1, is going to flip up to -1, +1. 0, 0 stays. And the point +1, +1 is going to flip down to +1, -1. Okay. And so now we're still going to draw this curve, but we need to make sure we're doing the curve in the right direction. That's a little bit awful. Let's try that again. Slightly better. All right, so that's our new curve. And you can see the blue curve that we had there originally, basically we just flipped it over the x-axis, and that creates the curve in red. All right, so that's the end of that P of x function. Let's go ahead and slide to the right here. So W of x. We have another negative sign here, but this time the negative sign is inside the parentheses with the x. So what translation is that? What actually transformation is that? Well, that's going to be a reflection over the y-axis. Okay, so because it's reflecting over the y-axis, this value right here, this point in the on the right, is going to flip over to the left. The point on the left is going to flip to the right. The way we're going to do that is we're going to flip the sign of your x value. And you could do that by saying you're going to multiply. Apparently I can't spell the word multiply. All right, multiply the x value by -1. Okay, and no change to y. Okay, so when you're reflecting over the y-axis, the y values don't change, it's the x values that are going to cause the change. So we're going to take our x values here, here, and here and multiply each and every one of them by -1. That will flip your signs. So -1 here is going to become +1, but don't change your y value, so -1. We're going to take 0 times -1, which conveniently will still stay 0. Don't change the y value. And then positive 1 here, we're going to flip its sign, make it -1, leave the y value alone. It's 1. So this point, -1, 1, is going to flip over to the right side of the y-axis, and it's going to become 1, -1. 0, 0 doesn't change, and this point is going to flip over here and be the point -1, +1. Curve on in here and curve on in here. So this part of the curve reflected to the left to become this piece right here, and this piece down here reflected to the right to form that part of the curve. Now you might notice and look at this and say, they're the same curve, Miss Curran, and that's true. All right. So this particular power function, now that's not always going to be the case, but in this case, for this problem, yes, reflecting over the x-axis is the same thing as reflecting over the y-axis. But don't assume that's always going to happen. All right, let's go ahead and move on. We're going to start talking about our dilations. Okay. So we've got q of x here is equal to 5 times f of x. So if your function is being multiplied by something, so this case it's 5 times f of x, this is a vertical stretch by 5. Okay, so what that means is when we go to deal with this, it's a change vertically. So vertical changes don't have any effect on our x. All right, so no change to x. But when we stretch vertically, we're going to multiply by, sorry, hold on one second. Multiply y by 5. I wanted to be specific on what I was multiplying. So every one of our y values needs to get multiplied by 5 to make this stretch work. Okay, so function value -1 here for the x isn't going to change. -1 times 5 is going to be -5. 0, 0. 0 for the x stays the same, and then we're going to take 0 times 5. Well, that still stays 0. The x value stays the same as 1. 1 times 5 is 5. So this point, -1, -1, is going to stretch further away from the x-axis, and it's going to end up all the way down here. 0, 0 won't move at all. And then this point, 1, 1, is going to stretch away from the x-axis all the way up here. So this curve looks like this, right? It's really, really stretched out. All right, so with a vertical stretch, you are literally pulling all of your points further away from the x-axis. Now, those points could be pulled low, further down, or they can be pulled up. So whichever way it needs to go, that's a vertical stretch. Okay. All right. But what happens when we multiply our function by a number between 0 and 1? So some kind of fraction or decimal value that's less than 1. Those are vertical compression by, in this case, 1/2. Okay. So how do the coordinates change? Well, vertical changes do not affect x, so no change to x. And a vertical compression here, we're going to multiply y by 1/2. Okay, we're going to push all of our points closer to the x-axis, in this case by 1/2. So -1 for the x value stays the same, But our y value here, -1 times 1/2, is going to be -1/2. So leave x alone. 0 times 1/2 is still 0. Leave x alone. 1 times 1/2 is 1/2. So this point of -1, -1, I'm going to push just a little bit closer. I'm basically going to chop the distance from this point to the x-axis in half. So my point's right here, and I'm going to take this point and chop its distance to the x-axis in half. So right here. Now it doesn't look like it did much, but basically what's happening is we're going to stretch this curve something like that. Kind of flatten the curve out as we go. All right, so that's considered a vertical compression. All of these points on the blue curve got pushed closer to the x-axis, so we've compressed them. All right, so those are your vertical compressions and stretches. Let's talk about the horizontal ones. Okay, so we've got 2x here, which is right inside the parentheses, right? It's right up next to that x. So describe the translation in words. This is, again, the horizontal ones are where it gets goofy. So this is actually a horizontal compression. Yes, I said compression by the reciprocal of what's inside with x here. So the reciprocal, remember, is just a big word that means flip the fraction over. So the number right here is 2. So the horizontal compression would be 1/2. All right, so it's the reciprocal. Now, horizontal values affect your x. All right, so in this case, we're going to multiply x by 1/2. But horizontal compressions will have no effect on x. So no change to y. I said it wrong at the time, sorry. So we're going to multiply x by 1/2, leave the y values alone. So this is going to be -1/2, -1. Multiplying 0 times anything doesn't change it, so still 0, 0. And then +1/2, 1. So this point, -1, -1, is going to push a little bit closer to the y-axis here. We're going to press closer to the y-axis. So we're going to go -1/2, -1, 0, 0 stays. And then this point, 1, 1, is going to compress just a little bit closer, right? We're going to chop that distance to the y-axis in half. And we're going to basically push those points closer to the y-axis. So let's see how good of a drawing it gets. All right, close enough. All right, so it gets the idea across in terms of what this graph looks like. So again, horizontal, kind of weird, but make sure you're focused on what's happening to the actual points. All right, last one for this particular video. This is going to be n of x. And in this case, we've got n of x is equal to f of the quantity 1/2 x. So we are dealing with something that is directly attached to x here. And it's a number between 0 and 1, which this is going to be weird, but this is actually a horizontal stretch by, again, what's the reciprocal of 1/2? The horizontal stretch is going to be by 2. All right, so that means we're going to multiply the x values by 2, and horizontal changes don't have any effect, so no change to y. Okay, so every one of these x values we're going to multiply times 2. So -1 times 2 is -2. Leave the y value alone. 0 times 2 is still 0, leave the y value alone. 1 times 2 is 2, leave the y value alone. So this point, -1, -1, has been stretched, right? It's being stretched away from the y-axis to right here. So -2, -1. 0, 0 can't stretch away from anything or compress close or anything. It's already the origin, so we're going to leave it there. And then this point, 1, 1, is going to stretch away from the y-axis to right here. Okay. And so let me see if I can draw that in, about like that and like that. Okay. So this particular video has dealt with your reflections and your vertical and horizontal stretches and compressions. If you've got any questions or concerns, please send me